Hello everyone. In this presentation, we are going to learn how a biosignal processing can be done using the TIVA Launchpad microcontroller, as we see here. So the biosignal which was taken here is a PPG signal, which is taken from the PPG sensor. So what is PPG sensor? So there is an infrared LED as well as there is a photo detector. With the help of infrared LED and the photo detector, we are able to find the volume of the blood flowing in the blood vessels. Based on that, some signal is generated. From that signal, we are able to find out the different biological parameters. In our case, we are going to find out the pulse rate to start with. So the PPG sensor, which has to be connected to the TIVA microcontroller launchpad, and then we are computing the pulse rate, and then we are monitoring the pulse rate. So this is the fundamental block diagram. So instead of PPG sensor, we are taking the PPG signal from the source called PhysioBank ATM, as you see here. So there is a data set available in the PhysioBank ATM. In this PhysioBank ATM, we can able to download our PPG signal. So from the downloaded PPG signal, we can do the signal processing much better. That is what we are going to discuss now. So here if you see, so what is PPG signal? As told, the source is a PhysioBank ATM. The sensor uses the infrared light to measure the volume variations in the blood circulation as an indicator of the cardiovascular systems. So after taking the PPG signal from the PhysioBank ATM, we are going to do the pre-processing, and then finally we are going to do the autocorrelation function, and then we are going to normalize it, and the normalized autocorrelation waveform looks like this. So in short, I am just briefing about the process of how to find the pulse rate of the PPG signal. So to find the pulse rate of the PPG signal, so we have to find the autocorrelation, and we have to normalize the signal. After normalizing the autocorrelated signal, the waveform will look like this. As we all know, finding the autocorrelated functions at 0 is the maximum peak, and then slowly it is a decaying signal, as we know very well. So the Rxx of 0 is the energy of the signal, right? Rxx of 0 is the energy of the signal, which is the peak signal, first peak signal. So to measure the pulse rate means we have to find out the second peak. So the time interval between the first peak and second peak will help us to find out the period of the signal, and from that we can able to find out the pulse rate. So how to find out the period of the signal, that is what we are going to discuss now. So the autocorrelated waveform looks like this. From this autocorrelated waveform, we have to find out the first zero crossing point. As you see here, we are finding the first zero crossing point, and after finding the first zero crossing point, the samples next to the first zero crossing point will be taken in the next window. As you see here, will be taken to the next window, and from there we are able to find out we are finding the second peak value. So we are computing the second peak value. So totally we have taken the 1000 samples. Totally we have taken the 1000 samples from the PhysioBank ATM, and those 1000 samples are plotted like this. And the first peak is very clearly observed, and the second peak is identified by finding the first zero crossing point, and we are taking separating the second window, and from the second window we are training out the second peak value. So after finding the second peak value, so say for example, the sampling rate of the signal is around 100 Hz. So because the sampling rate is 100 Hz, so every sample is of 10 millisecond interval. Every sample is of 10 millisecond interval. So finding the corresponding sample and then finding inverse of that will help us to find out the period. That is what we are going to see here. So the sampling frequency of the PPG signal is 100 Hz. So sampling period is again 10 millisecond. 10 millisecond is the period. So the time interval between the first sample and the next sample, like this, there are 1000 samples here. So this is 1000 sample means this is the first sample, second sample means time interval between first sample and the second sample is 10 millisecond. That we need to understand. So after finding this, then we are finding the first zero crossing point. So with respect to our sample signal, the first zero crossing point occurs at the 13th sample. First zero crossing point occurs at the 13th sample. and this second peak occurs at the 75th sample, that is from here. So considering this is 0 point and this is the 75th sample, and the previous window is again 13 samples, so 13 plus 75, 88th sample. So the first peak is at 0 and the second peak is at 88th sample. So the 88th sample means the 88th sample we get the second peak. So time interval between the first and second peak is the period of the PPG signal. So pulse rate. So what is the pulse rate? So 60 divided by the period, 60 divided by 88 into, that is 88 samples into 10 millisecond, which is 0.880 seconds. So 60 divided by 0.880 second is equal to 67 pulses. So the sample signal which was taken from the physiobank ATM has a pulse rate of 67. That is what we are going to find out through this coding, which we are going to see now. So as we all know, this is the Energia environment which is used for the programming the TIVA microcontroller. And the steps what we have discussed is very clearly given. As we see here, this program takes the PPG value and computes the pulse rate as follows. As we see here, we have to take the first 1000 PPG samples. That is what the 1000 PPG sample as a CSV values. What is CSV value? Comma separated values. And then we have to compute the autocorrelation function. So find out the similarities of this periodic signal, and then we have to normalize the autocorrelated signal, and then as told we have to find the first negative zero crossing point to find out the second peak and construct the new window from the first negative zero crossing point plus 1 to the end as discussed, and finding the peak value in the new window and finding the distance between the second peak and the first peak, and then computing the pulse rate is 60 by t and displaying the first negative zero crossing point and the peak value, that is the K max value, and then the period of the signal and then the pulse rate. So that is what the steps we are going to do now here. Then slowly if we see the code, so we have taken the integer, as integer is 1000, that is total number of PPG samples are 1000, and the 1000 samples are taken as a float variable as x of n. As x of n, as you see here, those 1000 values are comma separated values which are read from the PPG source, that is PPG source is your physiobank ATM. So after taking the 1000 samples and we are finding the autocorrelation function. So these are all the variables, right? As you see, these are all the variables. Float Rxx of n is nothing but the autocorrelation function of then normalized autocorrelation function value and the new window autocorrelation function values. These three are the variables, and there are some integers like first negative zero crossing point and then the pulse rate and then the period, and the second peak is identified with the help of the float variable K max value as per the discussion. And here you can see the serial window is initialized with the 9600 baud rate, and then so first we are computing the autocorrelation function. So how to find the autocorrelation function? So autocorrelation function for the value n is nothing but the 1000. So for the 1000 samples you have to find out the autocorrelation function. As we know, autocorrelation function is we are creating the for loop for integer n equal to 0, n less than n minus k, n plus plus autocorrelation function Rxx of k plus equal to x of n into x of n plus k. So this for loop helps us to find out the autocorrelation function, and then plotting this particular Rxx of k will help us to get the plot waveform as like what we have seen in the notebook. And then after that normalizing. So how to normalize it? So Rxx of 0 is the maximum energy of the signal. So normalized value of the autocorrelated signal is achieved by dividing the energy of the signal, that is Rxx of 0 signal, with all the signal values, which will help us to find out the normalized autocorrelation function, which brings the values between +1 and -1 as shown. So now the signal was taken and the autocorrelation was done and it was normalized, and then first we have to find out the first negative zero crossing point. How to find the first negative zero crossing point? And first how to find out the first negative zero crossing point? So this is one sample and this is another sample, this is another sample, this is another sample means. So if you subtract this sample minus this sample means it is positive value. If you subtract this sample minus this sample means it is positive value. And if you subtract this sample minus this sample means it will become negative value. So the last positive value and the first negative value is the best way to identify the zero crossing point. That is what we have done here in this coding. So the normalized value of I, the sample of I which is greater than 0, and the normalized value of I plus 1 which is value less than 0. So this is the very simple way to identify the first zero crossing point. So the previous value is greater than 0 and the next value is less than 0 means in between these two samples there is a zero crossing occurs. It's a very simple way to identify, and then we are taking that index. We are taking that index I as the sample value. At that sample only there is a negative zero crossing occurs. From that sample we are going for the next window to find the next peak. Yes or no? So from that sample we are going for the find out the next peak. For how to identify the next peak? So if you look at this for loop, in the for loop, here you can see now we have identified the first zero crossing point, and then this window, this window was separated, and then for this separated window we have to find out the second peak. How to find out the second peak? First zero crossing point plus 1 to n. We have to find out this remaining values. That is what you can see here. So for first negative zero crossing point plus 1 to the 1000 samples. Totally there are 1000 samples, and then we are finding out the new window. There is new window of, for the new window we are finding out the normalized value. So this normalized value is taken as a new window separately. So this new window, to find out the second peak, is being created, and then we are finding out the second peak with this for loop. So how to find out the second peak? Simply we are keeping the maximum value as 1000, and then we are using the for loop with first negative zero crossing point plus 1 plus up to n, and then we are finding the k max value. This k max value is nothing but the second peak value. So we are comparing the second. As of now, initially the k max value is minus 1000, and then first negative, the first window, the first sample of the first negative zero crossing point value is compared to the k max value. Definitely this value will be greater than this, so this value will be kept as a k max value. So all the remaining values from the first negative zero crossing point to the end sample will be compared with the k max value. The maximum value among the remaining values will be taken as a k max value, which is nothing but the second peak of the signal. So after that we are finding out the period. So how to find out the period here? And so here the distance between the first peak and second peak. How to find the distance with the first peak and second peak? Here we are finding out the integer. So finding out the integer, where finding out the point I where we are getting the k max value. So here at this point I, that is at the sample of 89th sample, we are getting the second peak. We are getting the second peak. That is what. So that is stored in the variable period. That is stored in the variable period, and then we are finding the pulse rate. How to find the pulse rate? So we are creating a new variable called float variable st. As we know, the sampling frequency is 100 Hz. So 0.01 into the corresponding period. So the pulse rate equal to 60 by t. 60 means pulse rate means number of pulses per second. Sorry, number of pulses per minute. So that is 60 divided by the time period of the between the two peaks. So as per the computation, as we see, pulse rate equal to 60 by t. As we see here, pulse rate equal to 60 by t. T is 88 samples as per the theoretical calculations into 10 milliseconds means you are supposed to get 67 pulses after running this code. And then we are printing this first negative zero crossing point, and then we are printing the second peak value, and then we are printing the period of the signal, and then we are displaying the pulse rate in a serial window. Now this is the TIVA microcontroller board, and then we are running this code. We are downloading this code and then we are running. So there are 4 parameters. So FNZZP is the first negative zero crossing point, which happens at the 13th sample. First negative zero crossing point is happening at the 13th sample, and the second peak value, that is the second peak value. So what is the first negative zero crossing point as per our discussion? This first negative zero crossing point occurs at the 13th sample, that is what's shown. Because it is normalized, the first peak is 1. As we all know, the first peak is 1 because it is normalized plus 1, because the values are between plus 1 and minus 1. The first peak is 1, and as we know, decaying function is the autocorrelation function. So the second peak will be less than 1. So the second peak value, we need to know this is a K max value. K max value is the second peak value, which is around 0.86. Here, that is what available here. K max value is 0.86. And then the period is 89. How do we measure the period? How it becomes 89? First 13. So from the 0 point to the first zero crossing, there are 13 samples. And then from the first zero crossing point to this peak, we are getting 75 samples. So 75 plus 13, which is equal to 88. So that is what 88 is displayed here as 89. Okay, 89. And the period pulse rate is 67. So from the PPG signal, by measuring the time interval between two peaks, we are able to find out the pulse rate. This is how pulse rate is identified, and then pulse rate is getting displayed as 67. So the entire computation is happening in the TIVA microcontroller.